Okay, we're going to start 14.3, which is all about partial derivatives. So obviously this is a calculus course, so we're going to need some type of derivatives. And the question is, how do we take derivatives in several variables? Well, let's just take one example. Let's just take a surface here. So let's have, say the surface is kind of a wave in the, that's a wave in the y direction. So let's take a point, say some point right here. We draw that in white here. Let's take a point in the xy plane, x naught, y naught, so that its image is somewhere here, which is the point x naught, y naught, f of x naught, y naught. And you say, okay, well, what does a derivative mean? Well, first off, remember that a derivative is a change in the function value as you move away from a point. So for example, let's say I move in parallel to the y direction. Let's say I move this way. So I'm moving, let me just describe this. I'm moving sort of parallel to the y axis. So I'm essentially changing just the y value. Well, what does that map up to? If I just change in the y value, I end up with, I'm essentially looking at this curve right here, which is the image of, if you sort of extended this line off, if you take this line right here, its image would be that image right here. So you could say, okay, what is the change along that direction? So we're looking at the change in essentially the y direction. Well, if you were traveling to the left, you would be going upward. And if you're traveling, let's just say you're traveling the other way, because let's assume we're going to be traveling in the positive y direction. Right now we're traveling in the negative y direction. Let's travel in the positive y direction. You would say, oh, I'm going downhill. So let me just write that down. Change in y direction is essentially would have a negative derivative, negative slope, aka negative derivative. Well, let's make this a bit more precise. Let's just look at that curve alone. Let's take that curve. So let's take that curve. That's what we drew there, and this was the point somewhere here was the point x naught, y naught, f of x naught, y naught. Let's move a little in y. So let's say we were at the point, remember the x here is constant, so you have x naught, y naught plus h, and then f of x naught, y naught plus h. So in this above picture, this would correspond to, say, a point somewhere here, which would be x naught, y naught plus h, and that would map up to a point up here, x naught, y naught, y naught plus h, f of x naught, y naught plus h. Okay, that's what we're looking at. We're looking at the change in y. Well, we can do the exact same game here where we draw the secant line. So the secant line would be something like that. And the slope here, the slope would be f of x naught, y naught plus h minus f of x naught, y naught divided by y naught plus h minus y naught. And that would be just f of x naught, y naught plus h minus f of x naught, y naught divided by h. And this should look somewhat familiar. It looks very similar to the definition of the derivative in one variable, except we have this extra variable sitting around. And this turns out to be exactly the definition of the derivative in multiple variables. So let's make now a definition. I only did it in the y direction. You could do a similar game in the x direction, but let's write down the definition. So suppose a function f of xy is given, and we have a point x naught, y naught in the domain of that function. We'll call that D. Then the partial derivative, it's partial only because it's in one direction. The partial derivative of f with respect to y at x naught, y naught exists if the limit as h goes to 0 of f of x naught, y naught plus h minus f of x naught, y naught divided by h exists. And if it does, we call this limit, so this thing has a name. This is called, well, there's two notations. There's del f, del y, which is the partial. So this little d-like looking thing, it's called a del. It's a little Greek symbol, del f, del y at x naught, y naught. It's also the same as f sub y. We put a little y at the bottom at x naught, y naught. Okay, so this is the partial derivative of f with respect to y at the point x naught, y naught. And similarly, the partial derivative of f with respect to x at x naught, y naught exists if the limit as, h goes to 0 of f of x naught plus h, comma, y naught minus f of x naught, y naught divided by h exists. And this derivative, this is called the partial derivative of f with respect to x at x naught, y naught with the del symbol. It's also labeled as f sub x of x naught, y naught. Okay, so let's compute. Let's just do a basic computation. So let's compute del f del x, the partial derivative with respect to x, and the partial derivative with respect to y of f of xy equaling x y squared at the point, say 1, 2. Okay, well, before we do 1, 2, let's just do it symbolically. Let's do at the point x naught, y naught, and then we'll plug in a couple of points at the point x naught, y naught. So we're looking at the limit as h goes to 0. Let's first do the partial with respect to x. So we have x naught plus h, comma, y minus f of x naught, y naught, y naught divided by h. What is this? This is x naught plus h times y naught squared minus x naught, y naught squared divided by h, limit h goes to 0, and this is just h y naught squared divided by h, limit h going to 0, and this is just y naught squared. So the partial of f with respect to x at any point x naught, y naught is equal to y naught squared. More generally, usually the way we just say it is del f del x at xy is y squared. This is, we usually kind of, we omit the base point because we want to find a general formula for the derivative. Sometimes we're going to plug in a point, sometimes we're not. So in this case, if we're going to plug in the point 1, 2, we simply, we plug in y equals 2 and we get 2 squared, which is 4. So the partial derivative of f with respect to x is 4. So if you're moving in the x direction, so if you're moving in the x direction from the point 1, 2, you'd be ascending. Moving in the, I should say, the positive x direction from the point 1, 2, you'll be moving upward, or kind of uphill in a way. Okay. Similarly here, let's compute del f del y, and I'm just going to use xy. Okay, so I'm going to omit the base point here because we're going to find a general formula, and then we'll plug in the 1, 2 at the end of it. So we're looking at the limit as h goes to 0 of f of, now we fix x, but we vary the y plus h minus f of xy divided by h. This is by the way, this is the more general version, just because it's not at a particular point, but at any general xy. What do we have? We have limit h going to 0 of x times y plus h squared minus xy squared all over h. This is the limit as h goes to 0 of x y squared plus x, or I guess 2x yh plus xh squared minus xy squared all over h. And we end the xy squareds cancel. We get h times 2xy plus xh divided by h. Limit is h going to 0. And the h's cancel. We end up with just 2xy. Okay? So there's a couple of important things here to note. Before we do that, if we just plug in now the point 1, 2, we end up with del f del y at 1, 2 is equal to 2 times 1 times 2, which is also 4 in this case. So what are some important things here to note? We started off with f of xy being xy squared, and then we found that del f del x was y squared. The del f del y in general was 2xy. Well, when we did this, note that here for del f del x, y squared was like a constant, was essentially a constant term, in the sense that if I had let's call it in one variable, if I had g of x being, say, 3 squared times x, g prime of x would have been 3 squared. So the y squared term acted like a constant. In a similar way, when I have del f del y, this was, here x was like a constant. X was constant, so del f del x is similar to if I had, say, g of x being, let's call it g of y, so it's the same variable. If I had g of y being 2y squared, g prime of y would be 2 times 2 times y, or 2 times 2y, where this guy was similar to sort of the x in the original f function. So this, replace that. So that's a kind of a general principle that reoccurs, and it allows us to easily compute more general partial derivatives. So let me just conclude here with one example, which is a bit more complicated. So let's take f of xy being sine of x squared y plus y cubed. And let's directly compute the partial of f with respect to x and the partial of f with respect to y. And then we'll end this video there. So del f del x, well, again, what are we thinking? We're taking the derivative with respect WRT with respect to x while viewing y as constant. And that's exactly what we did even in the picture. When we initially derived the formula, we fixed one of the variables and varied the other one. So this is now, how do we think of this? This is cosine of x squared y plus y cubed times the chain rule, the partial with respect to x, so del x of x squared y plus y cubed, right? This is how we think of, just like the same way we did one variable derivatives. And again, since y is a constant, del x of y cubed is 0. So we get cosine of x squared y plus y cubed times, we get 2xy plus 0, because the derivative, if y cubed is like a constant, the partial with respect to x of that is going to be 0. So we end up with just 2xy cosine of x squared y plus y cubed. Okay, so I'm going to leave you here. So a little exercise that I'll do next is compute the partial of f with respect to y for this same example. And again here, f of xy is sine of x squared y plus y cubed. And in the next video, we'll do a few more computational examples just so we get comfortable with taking partial derivatives. Okay, till next time.